So good afternoon and welcome to the Portland State University Center for Transportation Studies Friday Transportation Seminar. And my name is Rob Bertini, and I am very pleased to, on behalf of myself and my colleagues, Chris Monsieur and Jennifer Dill, first we want to thank the Oregon Department of Transportation for sponsoring this seminar. And we are very happy to welcome Professor Nigel Wilson from the Massachusetts Institute of Technology as our visiting scholar today. And I'm going to turn it over to Nigel, and I want to thank you for joining us here today.
Visit here possible. This is my first time in Oregon, first time in Portland. As I was telling some people earlier, it's like first visit to Mecca. It's hear about Portland in so many positive contexts for so long. It's very exciting to have the opportunity of being here in person and seeing it. What I'm going to be talking about today, and I'll give you a little bit more of a background on who I am, but what I'm going to be talking about today is one aspect of the research that I'm involved in now on public transportation. As Selman mentioned, we've had a program at MIT and partner universities, including Northeastern University, for about 10 years, doing applied research in urban public transport, covering a whole host of things from physical design of stations to operations management and control to policy, finance, a very broad program in which we've had a lot of students going through this, learning about urban public transport and doing internships, and many of them going on to positions either in consulting firms working on urban public transport or to work directly in agencies themselves. Again, one of the things that made me very excited about coming here is to see firsthand the relationship between Portland State University researchers and TriMet. I think this is a model that we've looked at MIT as being a very effective example of academic transit operating agency cooperation, and we've been involved in some similar cooperative relations with Puerto Rico, helping them build a heavy rail line, and currently with Chicago, the Chicago Transit Authority, helping them rebuild 3 of their elevated rail lines, and currently with the MBTA in Boston, helping them think through the planning and design of their first BRT, bus rapid transit facility called the Silver Line. Just to give you a few words about who I am, as you will have guessed a little bit from my accent, but certainly from my first name, I'm not a native U.S. Citizen. I'm originally from the UK, and I've been at MIT, however, for, this is my 40th year. Yeah, I've been here for 39 years, so this is my 40th year, man and child, but I've been on the faculty for about 35 years of that. And I focus on urban public transport, and I also am active in a whole range of professional activities, which I won't get into here. Okay, so thank you all for coming, and I look forward to a discussion after I go through this. Let me first of all acknowledge the work that 2 of my current and ex-students have done, which this is really built on. The first student I'd like to acknowledge is Jinhua Zhao. He's currently a doctoral student in urban studies and planning at MIT, just finished his MST thesis working with me, and much of this presentation is based on his Master of Science in Transportation and MCP thesis that I supervised. And the other student is an ex-student, Adam Rabi. Some of you know Adam. He works at the Chicago Transit Authority in rail operations and came through the MIT program and worked with me on his Master of Science in Transportation thesis. If you want more information on what I'm going to go through, and obviously I won't go through all aspects of this because there's a fair amount of work involved, the reference that I put up here is Jinhua Zhao's master's thesis, which is available, and I can certainly send it to you electronically if any of you would like to get a copy of it. I will give you my email address, just so if you want to be in touch with me, nhmw@mit.edu. And so if you've got any questions about what I cover after the fact, feel free to send me an email, and I look forward to interacting with you. Okay, so what am I talking about here? What I'm talking about is actually very closely related to some of the work that Portland State University has been doing with TriMet on the general issue of extending the value of the data that we get from automated data collection systems in urban public transport. I'll be talking about a couple of different applications because I don't want to do similar applications to the ones that Portland State and TriMet have been doing jointly, which I think are very impressive, and I think we're trying to emulate what they're doing in some of these areas, but we'll see some slightly different applications. But the general objective I have here is seeing how we can squeeze more valuable information to support decision-making in an agency from these increasingly ubiquitous automated data collection systems that we have. So I want to talk a little bit about the general premise, then spend most of my time on two case studies. The first one, they both deal with the Chicago Transit Authority, also known as CTA. The first one deals with estimating passenger movements in the CTA rail network and what the implications of the approaches we've taken are. And the second one deals with estimating how people choose paths in the CTA rail network. And for those of you who haven't been to Chicago, it's a fairly complex rail network, and I'll give you a little bit of background on that. And then talk at the end about where we might go in general, not just at MIT, but more broadly, thinking about how we can build on the work that we've covered, that we've done already. So I think we're all aware that transit agencies are at this exquisite transition point from being very data poor to being embarrassingly data rich. And so those of us who've been involved in research in public transport for some time have to readjust our frame for thinking about what the critical challenges are. Previously, the critical challenges were, how do we gather enough information at reasonable cost to be able to understand the way the system is functioning? That's no longer such a critical issue, because we have lots of automatic data collection systems that can, if we're clever, can tell us a lot about the way the system is operating. Now, the way we want to help make decisions there are many ways, and certainly one of those is to understand what contributors to poor performance might be and develop strategies to improve performance in the short run or through investments in the long run. And so understanding more about the current state of the system isn't the whole story, but it's a very important starting point towards improving service and improving the urban environment overall. So what I've tried to characterize here is the sort of traditional manual sorts of data collection, low capital costs. These are people going out and doing counts. I'm sure many of you have been through this. I certainly have, and have the scars to prove it. These are characterized as, the good thing is they're cheap. It doesn't cost very much to give you your counter or whatever it is, whatever the low-tech aid is. But they're very high marginal costs because you pay for every, unless it's student labor, of course, you pay for every hour of data that you're collecting a fairly high price. This tends to drive you towards small sample sizes, which means even if you've done your very best to be representative, you may not have a really good picture about how things operate. The data tends to be quite aggregate. They're not individual observations you have. It's often subject to measurement error, biases. It's unreliable. And it's limited spatially and temporally. If we look at automated data collection systems, we potentially can cure many of these problems. We're going from something which is high marginal cost to something which is low marginal cost. Once we've acquired the system, the additional cost of getting information is data anyway, is quite low. Cost of information may be another issue. We can very easily get very large sample sizes. Look at every bus trip run on a route in a year or in any period of interest. We can get much more detailed disaggregate data on the attribute of interest. And we can, while we'll still have errors and biases, we're in a better position to quantify what those errors and biases are and to correct for them. So I think it's important step in getting us a better picture of the way the system is really functioning. So the sorts of systems that I'm referring to here are automatic vehicle location systems, which are tied in many cases with bus dispatching systems, such as, of course, in the case of TriMet. APCs, or automatic passenger counting systems, and AFCs, automatic fare collection systems. And here in Portland, in TriMet, we have AVL and APC systems, not yet advanced AFC systems. So if we look at the potential and the reality here, the potential for automatic data collection systems, we have an integrated ADCS database. We have software to support many agency decisions based on the ADCS database. We can obtain insight into things that we couldn't normally ever hope to assess. For instance, what happens in extreme weather situations? What happens when we have major sporting events? What happens when we have, what happens on Sundays? We often, in manual data collection, Sundays don't exist in terms of data collection. It's too expensive in terms of the return. So ADCS fundamentally changes our ability to assess what's happening under a range of different situations. The reality, and I'm not talking about Portland TriMet reality, I'm trying to be fairly general here. Most ADCS systems are implemented independently. Sort of, we look at an automatic fare collection system independently from the AVL system or the APC system that may also be present in the agency. The data collection is often ancillary to the primary ADC function. So for automatic fare collection, the primary function, the reason you have the AFC system, is fare collection and revenue protection. Data collection, well, that's a nice fringe benefit, but we don't often design the systems effectively to accomplish that because it's not one of the primary objectives. And AVL, originally anyway, I think was largely for emergency notification, what happens if we have a major incident on a bus, and also increasingly for stop announcements. Portland TriMet's going through the process of automating the stop announcement system to be in full compliance with ADA. Many other agencies are going through a similar sort of thing. So while we can get valuable data out of these and other automatic data collection systems, data collection is not the primary objective. And often we have to work pretty hard to squeeze out the information we want. As a result of this, many problems are there to be overcome if we're going to get the full value. It's not easy to integrate data, often, because of the way the systems have been spec'd and implemented, and it requires substantial resources, both human resources and monetary and computer resources to accomplish this. And often the challenge we have is making the case within the agency that it's a very important activity. And again, I'd cite TriMet as a great example of an agency that's really committed to getting a lot of valuable information out of the ADCS that exists. So what I'm going to talk about in the case studies are two examples, both from the CTA. The first one is looking at the estimation of passenger movements in the rail network. So we can think of this as OD matrix inference and analysis. It's inference because we can't measure these things directly. We have to be fairly clever and make some assumptions to obtain some estimate of the OD matrix. The second one is rail path choice decision modeling. So what's the situation with the CTA in terms of their implementation of automatic data collection systems? Well, they have a pretty advanced automatic fare collection system. So it's a mag stripe system with basically a small number at this point of smart cards. Eventually, the idea is that more and more of the mag stripe cards will be contactless proximity smart cards, but they're not very far up that implementation curve yet. They have automatic voice annunciation system for stop announcements, which incorporates a GPS system, GPS-based AVL, but it doesn't have real-time communications capabilities. So it can't be used for real-time control, but it can be used, obviously, for ex post, after-the-fact analysis. And we'll show how we've used that. And APC, currently it's on about 20 to 25% of all CTA buses, but it's being included in all new CTA procurements, bus procurements. Okay, so why are we interested in the origin-destination matrix for public transport passengers? Well, it's fundamental to our understanding of system usage, and it's a key input into the scheduling process and the planning process, all aspects of planning processes. Traditionally, it's available only from automatic fare collection systems, which have both entry controls and exit controls. So those of you who've used BART in the Bay Area, Washington Metro in Washington, D.C., those are systems which have exit control as well as entry control. So you can link a particular fare card through a unique identifying number from the origin to the destination. So you can determine the origin destination. It's measurable. For those of you who've been to London, London has a similar sort of system because it has a fare that's based largely on distance, and so you have to have exit control because you have to know where the individual entered to make sure the correct fare has been paid. But in fact, they don't have the ability in London to estimate, to measure the origin-destination matrices because the system is fairly, it wasn't designed with that in mind. So it's there, but in fact they use passenger surveys to estimate the origin-destination movements on the underground network. Bit strange. But certainly for CTA, for Boston, for most systems, you have entry control but not exit control. So you can't measure, you have to infer and use algorithms to estimate where are origin-destination movements. And for bus systems, again, ubiquitously, you don't have exit control. You just have entry control. So the challenge is to infer the OD matrix for entry-only AFC systems, be they rail or bus. It builds on earlier work at New York City Transit and also at CTA by Adam Rabi. And this is a building block towards estimating multimodal bus, rail, origin-destination matrices, which would be fantastic for any of these agencies, including Portland TriMet, to really understand how people are using the system, in what way, what range of ways they're using the system. So this is an important building block towards that. A couple of very specific applications that they're intending to use in Chicago. In Chicago, what they've done is to make redundant or reassign their manual traffic checkers, because they believe that through estimating the origin-destination matrix, we can estimate the passenger flows on each rail line by segment and by time period. That's what traffic checkers previously did. They stood at stations and made estimates of the number of people on board a train. So we can now infer this, and we don't need to spend this money on manual data collection. Similarly, if we know the origin-destination movement of a passenger, we can infer the path through the network and look at interchange volumes at specific transfer stations, and that can help in facilities design as well as other aspects of service planning. There are many other examples. So what's the basic idea here? Basic idea is pretty simple. The AFC card has a unique identifier on it, a serial number if you like. It has a transaction type. Are you using this to enter the system through a station, to enter a bus through a fare box? Are you recharging the card at a ticket machine? What's happening? What's the transaction that's occurring? What's the time of that transaction down to very, very fine precision? At what time did that transaction occur? And the transaction location. Which rail station? What bus? Specifically, what unit on the bus read the card? Okay? And we can hopefully trace that back to what route and what stop the bus was at when the transaction occurred. We'll talk about that more. So the basic information we have then is spatial information. We have a transaction for a single fare card at A with a location and time, at B with a location and time, at C location and time, and D location and time. This might be the full set of transactions for that fare card, i.e. implied for that passenger on a particular day. Okay, so we can then say, for many trip segments, although not all, the origin of a particular trip segment is likely to be the destination for many of the prior trip segments. Okay? It won't hold absolutely, but in many cases this will be true. So if we make that assumption, this allows us to identify trip segments. So this origin here has a destination at point B, which is the origin of the second trip segment. So this is trip segment 1. Sorry, this is trip segment 1. Similarly, this is trip segment 2. This is trip segment 3. Now, will this be true? Not clear. Sometimes it will, sometimes it won't. We have to be fairly careful about how we make this assumption. But what we've got is for each bus boarding, every time you board a bus, unless it's a proof of payment system, of course, which is another issue, but in CTA they don't have proof of payment, a TS for bus, a trip segment for the bus, represents an unlinked trip. An unlinked trip is just a vehicle boarding. So a trip segment here on bus would mean that you boarded this bus at this location, you followed the route, and you boarded the next bus at the same location you alighted at, which is at point B. On rail-to-rail transfers do not require a new AFC card reading. So there's no barrier in most systems going from one rail line, from one train on one rail line to another train on another rail line. So in that case, what the trip segment represents is a path on the rail network. It's not necessarily a unique vehicle boarding and alighting. So what are the assumptions for this inference method to be correct? Firstly, no intermediate private transportation mode trip segments occur. So if we go back to A and B, there isn't a private trip like a car or a taxi between getting off one vehicle and getting on another vehicle. Otherwise, that doesn't work. Our assumption is not correct. Secondly, passengers will not walk a long distance. Now, this is fuzzy. What's a long distance? How long is reasonable for people to walk? That might be different in Chicago and Boston and London. Probably is. And so this is sort of fuzzy logic. But this is sort of a general issue. And thirdly, the last trip of the day ends at the origin of the first trip of the day. So you can tie where I finished my trip tonight with where I'm going to start my next trip tomorrow morning. And that allows us to infer that last trip segment. These won't always be correct. These won't always be true. So we'll need to do some sort of validation on the inferences that we can make from this. if we look at the day trip segment chain, what's a day trip segment chain? This is the sequence of transactions of a particular fare card, presumably for a particular individual. Again, some people may transfer their fare card to someone else during the day. So that's another trap that we'll have here. But assuming that you hang on to your fare card and every transaction is your transaction, is your trip, then typical trip chains we'd have is RR, a rail trip followed by a rail trip, RBBR, rail transferring to bus, and then bus transferring to rail. Presumably this is at the beginning of the day, this is at the end of the trip activity, whatever it is, and then many others. So we use the following trip's origin to infer the previous trip's destination, as I said. And we have, in that case, we're looking at each couplet of trips, each successive sequence of two transactions. And we can have rail to rail, rail to bus, bus to bus, and bus to rail. In this particular application, we're interested in focusing only on the rail trip destination inference. We'll do the bus later on, but at the moment we're worried about the rail. That's hard enough. So bus trips can help infer the rail trip destination, the rail trip segment destination, if we have an RB sequence, like this one, RB. Then where the bus boarding occurred can help us infer where the rail trip segment ended. Okay? The technologies and the techniques that we're going to use here are, we use GIS. I think you're all familiar with GIS. We use this to compute walking distances on the street network. So we're operating on a street and transit GIS representation of the network, and to compute minimum paths in the transit/walk network, the combined transit-walk network. And we have AVL to identify the location of the AFC transactions on a bus route. And I'll talk about that more shortly. So if we look at the sequence of consecutive trip segments, we have somewhere here, where's the cursor? There it is. We have RR or RB. If we have if the consecutive trip segment is RR, then the rail trip information can be utilized directly, and this is, if you like, case A. If we have RB, the best case is we have GIS information and AVL information available, and we can fully utilize the bus trip information in this inference context. At the other extreme, we don't have any GIS information available for our inference, and AVL is not available for this particular trip for whatever reason, and then the bus trip information cannot be used because we don't know where the bus boarding occurred. We don't have AVL and we don't have GIS. We can't test whether it's a plausible walk connection between the rail network and the bus activity. So this is the best case, is the worst case, and the intermediate is we have GIS system, but the AVL is not available for that particular transaction, which we can make then partial inferences on. So let's look at the simplest case, rail to rail. So these are actual transactions for card number with serial number this on a particular day. The first transaction was reading the card at Central Park at 9:41:11. The second transaction, the only other transaction on this card, the next one, was at Sedgwick, and that was actually the only other transaction on this card for that day, which was at 14:01:26. So we can say, okay, Sedgwick then was the likely destination for this first trip, and using the wraparound theory, Central Park is the likely destination for the second trip segment, which started at Sedgwick. Okay? So to generalize from this, if the first trip origin is not equal to the second trip origin, but they're both on the network and you can make the connection, then we set the first trip destination to be the same as the second trip origin. Straightforward. If the first trip origin is the same as the second trip origin, then we have the multiple swipe case. In some systems, you can use a single card to swipe a number of people through. Now, obviously, that shouldn't work if it's an unlimited use card, But if it's a pay-as-you-go type of card, then that's legit. And so what you do there is you have a time window to say, well, if it's a multiple swipe case with a group traveling together, then the swipes will occur within some time window, and we can say everyone has, we can make the semi-heroic assumption that everyone's going to the same location because they all boarded it in a group at the same location. Again, this is inference. It's not absolutely guaranteed, and we need to worry about validation. Outside 3-minute time window, something else happened, and we can't infer it. In the RB case, let's look at GIS is available, but AVL is not available. We can partially use the bus transaction here. In the first case, we may have no practical rail-to-bus transfer. Okay, so there's no connection between the bus route on which the boarding occurred. There's no point of connection, and the rail network. We've got a problem. We can't infer it. We have a unique rail-to-bus transfer transfer point. In other words, there's only one point of intersection between the rail network and this bus route. That means that must have been the location at which the transfer occurred. Okay, so we know where the boarding occurred, even though we didn't have AVL information for where the bus was. We can infer where the bus was because we know what route the transfer occurred to. So the destination in this case can be uniquely referred. If there are multiple rail-to-bus transfer cases, then again we cannot infer the destination uniquely. So in this case, this is another actual case. These are all from January 2004 data. That's the time that the database that we were using for this analysis. So the rail boarding occurred at station ID 370, and the bus boarding occurred on bus route 17. There's only one point of connection between bus route 17 and the CTA rail network, which occurs at Forest Park Station on the Blue Line. That must have been the location where the transfer occurred. And so this is using only the GIS technology. If we look at having AVL data available, then we can now resolve the issue about where the bus was on the route, which has multiple possible transfer points. We look at where it was in terms of the AVL log and compare it with the AFC transaction time. And we can say, okay, that's where it was. So this is a case in point, an example of this. This is the origin. This is the bus route number 55, which has 3 different transfer locations to the rail network. The AVL records show it was here at 1408, here at 1420, here at 1435. And the AFC transaction occurred at, sorry, I'm confusing European time with North American time. I'm a split personality here, I admit it. So this occurred at 1420, okay? And so we can say, okay, well that must have been actually at location B. And so it was this was actually the location of the transfer point because we were able to tie in the AVL time with the AFC time. And this is an example, again, of integrating across databases. So on the AFC side, we have the serial number for the card, the boarding time, and the bus ID. On the AVL side, we have the bus ID, the time, and the bus stop ID, about where the bus stop was at a particular point in time. And so we can use the GIS to link the bus stop and the rail station and infer where the transfer occurred in a rail-to-bus trip. So in terms of what Jinhua did was develop some inference software. The input is the raw AFC data, raw AVL data, and various accessory tables to link where the AFC unit is to the bus that was operating with that AFC unit at that time. It turns out, at least in the CTA, some of the automatic fare collection units get moved from bus to bus at various points in time. So you have to have mapping tables, accessory tables or ancillary tables. The output is the inferred rail origin destination matrix for a sample of all passenger trips. You won't be successful on inferring every destination for every boarding. So the more successful you are, the happier you are, but we'll see what the actual results are. And this is practical in transit agencies. Specifically, what we're doing now with CTA is we're making this a tool that they can run on a daily basis within CTA, so that they can actually get, at the end of the day, the origin destination matrix for CTA rail travel on that day. That's the goal, and they're going to use this as a production piece of software. The performance in this case is pretty good. It took about 1 hour of computation time for a 5-day period rail origin destination matrix inference in the CTA. And what that means in terms of transaction, the total rail AFC transactions were 2.6 million records for that week. And in this case, the success rate, and I put success here in quotes because success doesn't mean that we were correct. It means that we were able to come up with an answer, which may or may not be correct. So calling it success is one view of success. So using this somewhat generous definition of success, we were successful on identifying destinations for about 2/3 of all the rail entries. And where these came from, 51% of the inferred destinations were based on rail-to-rail sequences where the next train trip was the same day. 33% were linking up the last trip of one day with the first trip of the next day. So this rail-to-rail sequence represents, 84% of all the successful inferences. That means that all of these RB sequences we're not being nearly as successful on the rail-to-bus transactions because, at least when we did this, the CTA AVL system is not nearly as advanced in terms of being up the learning curve as the TriMet one. We were only getting about 40% success in terms of the AVL matches. That we had about a 40% success rate in January of 2004 in terms of figuring out where a bus really was. Partly that was because not all of the buses had functioning AVL equipment, and in some cases the AVL wasn't functioning on that particular trip. I think we're all be somewhat familiar with this. So that's where we are on this first case study. The remaining challenge is expanding from the inferred destination sample to all rail passengers. So if we've got an origin destination matrix for only 2/3 of the travelers, that doesn't do us a lot of good in terms of estimating peak loads or total transfer volumes. So we have to be able to scale it in some way. And we're wrestling with that at the moment. One way is to say the singly constrained is we have control totals for each rail station in terms of total fare card and cash entries at the 15-minute interval over the day. So we could actually take the 15-minute inferred destinations and expand it by the unsuccessful inferences in that 15-minute period. So that's just treating the control total on entry controls. The other one is to make the assumption, which is pretty strong, that over the course of a 24-hour period, the number of exits at a station will be equal to the number of entries at that station. That most people are making round trips. Again, we're walking further and further out on the limb of this tree. We want to look at both of these and then do some validation to find out which one of these is actually more reflective of what's actually happening. But my personal view is that I think the singly constrained method is actually going to be a more robust method for moving forward with this in terms of the scaling. And then we need to do this validation of the accuracy to make sure that the destinations we're inferring are in fact correct. And that's very important, because at the moment all we'll have after scaling is hypothetical but not a verified origin-destination matrix. And if we're going to use this for decision-making within an agency, we have to have more confidence than that. So that's where we are on the first case study. The second case study, which isn't as long, sorry, but I congratulate all of you. I don't think anyone's fallen asleep yet. This is much better than I do at MIT, so my compliments to you on this. The second case study is CTA rail path choice. So in fact, in the CTA network, it's a fairly complex rail network, as I'll show you in a second. And in particular, you have this loop, this famous rail structure, which is an elevated rail structure in the heart of Chicago. And that gives you many options in terms of the path you take if you're traveling to and from the loop, as we'll see. And the challenge is to now, we traditionally understand assignment, transit assignment, or path choice in a transit network context by doing passenger surveys, either a VL choice or stated preference choice, and estimating a model based on that. So the challenge that we set for ourselves here is, if we could use this AFC data to actually get some insight into path choice behavior, hey, we'd be well ahead of the game in terms of really getting, again, squeezing more information out of this ubiquitous data source. And the approach we're taking in this case is we have limited direction of entry data on which we can infer the chosen path to the inferred destination. So we're stringing together some inferences here. So again, will this work? I don't know, but we want to estimate the model and look at the results and say, are these plausible results? And that's what I'm going to show you. So this is the loop. Okay, as you see, in the context of the rectilinear grid, it's a loop. So rail lines come in from the north, from the west, from the south, from the southwest, and trains go around the loop in both directions. Selman knows this very, very well from his summer in Chicago. So it turns out from many, if you board the CTA rail network at many stations, you have a choice of which direction to go in if you want to get to a particular destination. In this case, if you're traveling from LaSalle, which my eyes are terrible, but LaSalle is down here, that's LaSalle, to Midway. Midway is out on the orange line off the map down here. You have the choice of traveling westbound on the orange line, which means you get on here, you go all the way around the loop on the orange line, and then you go out to Midway. The alternative is to actually travel eastbound on the brown line at LaSalle until you get to Adams, where you can transfer to the orange line. So those are two choices. And those choices exist for many travelers from many loop origins to many non-loop destinations. It turns out that in this particular case, if you look at the data, and we actually have data about how many people boarded heading northbound or southbound, sorry, this should really be eastbound and westbound. This is the westbound case, eventually you go north. This is the southbound case, you go east and eventually south. In this case, it was 57 out of 153 took the orange line, i.e. went all the way around the loop and avoided a transfer, whereas about almost twice as many took the transfer to save the time from traveling all the way around the loop. So by looking at this behavior at all the stations in the loop where you have directional boarding information, you have a data set with actual behavior, actual path choice, from which you can estimate a model. And that's exactly what we did. So the data sources, one is the inferred rail origin destination matrix from the previous case study using AFC and AVL data. We have the attributes of the alternative paths. How long does it take you to go around the loop each way? And this is based on a Transcad GIS representation of the CTA rail network, including the transfer walking distances at specific stations, so you know how much time is involved and how much effort is involved to make the transfers. And we have, again, it's not complete path choice information, but we know at least the direction you entered the system at, so we can infer something about path choice. At 4 loop stations where AFC provides direction of boarding. So if you go through this AFC reader, you're traveling northbound. If you go through that one, you're traveling southbound. So it's, again, trying to use what limited information we can to stretch our understanding of behavior as much as possible. The independent variable groups that we had in this case, the basic variables that we included were in-vehicle travel time to get from your origin to your destination along each path. How much in-vehicle time is there? What's the initial waiting time? If there's a difference in frequency between the 2 routes you take initially, and the number of transfers. Clearly, the number of transfers will presumably affect path choice. The transfer attributes, transfer waiting time and transfer walking time, those we felt were likely to influence behavior. And the other trip attributes, total travel time, total track length, number of stops, all of these could perhaps influence behavior, but it wasn't clear that they really would. So these definitely, yes, almost certainly, but these are the attributes of the transfer station itself. So they relate to facility design. Very nice, yes. Well timed, well timed. It's okay. Again, this is the model evolution sequence, and again, I won't go through all of these models, believe me, I'll just give you one model. But this is the base model. Then we introduced the transfer attributes in another model. These are discrete choice estimations. We looked at model B plus the trip attributes in terms of length of trip, and then we looked at the interaction between model B and this is an interaction formulation of the model, and then we looked at taste variation, a discrete choice model. And again, I'll just give you one example, and I won't go through it in detail. This is one of this class of models where introducing the transfer attributes, but not one of the more complex ones. This is the adjusted rho squared, which is an overall measure of goodness of fit. Pretty good. These are the t-statistics for each one of these independent variables. It shows in-vehicle time and number of transfers are strongly significant, as is transfer walking time. Those are the significant variables here. The marginal rate of substitution between transfers and in-vehicle time is 6.88, which suggests that the marginal rate of substitution, one transfer is worth about 6.88 minutes of in-vehicle time in this particular case for this particular sample. Again, you wouldn't think you could estimate these things from AFC data, would you? But we did, whether it's true or not. But they're plausible numbers. And the marginal rate of substitution between walking time, and this is now transfer walking time. So it's walking in the transfer station between getting off one train and getting on another train, and in vehicle time, the marginal rate of substitution here is 3.4. So 1 minute of in-vehicle, 1 minute of walk time is equivalent to 3.4 minutes of in-vehicle time. Again, plausible numbers. They're not radically inconsistent with what other people have found in similar research. These are some different formulations. This is now with interaction terms as well, and these are this is the if you like to think of this is the transfer penalty measured in vehicle time. And if we don't include the transfer attributes like transfer walking time in model A, then a transfer is equivalent to about 9 minutes of in-vehicle time for typical Chicagoans, users of the rail system. If we introduce transfer walk time as a specific variable, that will obviously reduce the overall impact of the transfer penalty per se, because we've captured some of that impact in this term. And so in that case, this is reduced to 7.26 minutes. So the transfer walk time accounts for about almost 2 minutes of the transfer penalty. Okay? So that has some insight for transfer facility design, station design. And the final one is an interaction term, which is more complex, and I won't go into it in detail. We can get into it in more detail if you want in questions. But this, again, allows us to reduce the sort of the nut about how much is the intangible negative effect of a transfer. We can get it down to 3 minutes with this particular formulation. This is a potential application of this in a particular market segment. If we're thinking of doing rerouting on the loop structure, on the routing around the loop, which CTA is actually thinking of doing, and it would result in a change in the number of transfers on the northbound path from 1 to 0, this would be the change in the northbound share of that market. It would go from 30% up to 75%. If we could eliminate one of those transfers through rerouting, and obviously the southbound path market share would be reduced in the same way. So this is an example of how we'd apply the model to analyze rerouting options. Okay, conclusions. Automatically collected data has great potential. I think the work that TriMet and Portland State has done in the context of AVL and APC data has clearly demonstrated this. I think we've demonstrated this in the context of AFC data as well. I think AFC data provides significant marginal benefit beyond AVL and APC data. So it has great potential beyond the primary function for which it was designed and through integration of data from different systems. I'm a very strong believer that this data integration across different systems is going to provide us with a tremendous bonus if we're thoughtful about how we do this. Utilization is not straightforward. There's a lot of chains in the inference here. We have to really understand these and think deeply about them. But I think we will be able to learn a lot of new things about behavior at very little marginal cost. And I think that's going to be a tremendous benefit, and it will help us shape our surveys, which we'll still want to do, to complement what we're getting from the automatic data collection systems. It seems to me that will be a very useful improvement in the cost effectiveness of our survey instruments, our market research instruments. And we need certainly a strong foundation of data processing and analysis is required. And again, TriMet is an exemplar of having that real depth in terms of research, IT, and data processing skills. So in terms of future research directions, things we're involved in now, certainly the Rail OD inference algorithm validation. We're doing that now with Adam Rabi and others at CTA. It's very important. Extension from the rail to the full public transport system, including expansion to the bus system. We've begun to think about that. In that case, we'll have the APC data, which will be a very valuable source of feeding into this inference machine, which we didn't have on rail. I know you're getting some APC data now on your light rail system. Chicago doesn't have any APC information at all on their rail system. So it'll be a slightly different approach, but I think we can get some interesting results from that. Case studies of transit agencies with different ADC systems and challenges. Again, we're just about to start working with London on doing some of the same work with them in their very different context. One of the things about London is they're very far up the learning curve in use of smart cards. They have something called the Oyster card, which has 2.3 million users currently in London. So they're not as advanced as Hong Kong, but they're very well up the learning curve, and there's a very rich database. The advantage of smart cards as compared with magnetic stripe media is that smart cards stay with you for a long period of time. So you can trace behavior changes for individuals over a much longer period of time. And we're doing some of that work in Chicago with the Chicago card, which is nowhere near as ubiquitous, as I said, as the Oyster card in London. But it is another very useful form of inference about behavior. And finally, to integrate the ADC system data into long-term network modeling. All of what I've talked about and what we've been doing are precursors to getting real value out of this, which is how we improve the system, both in terms of infrastructure investments and in terms of operating plan improvements. Again, just the sort of work that TriMet and Portland State have been doing with AVL and APC data. I think we can begin to get some additional information and intelligence to help us improve the systems from incorporating smart card and more generally AFC data in the analysis. Okay, I appreciate your patience and I look forward to any questions you've got. Thank you very much.
And I'll remind people to use the microphone if you have one near you for your questions.
Yes.
Hi. In the case study 2 regarding the northbound or the westbound, eastbound, interested to find out which way actually is faster in general. There was about 2/3 of the folks that seemed to make the transfer, and about 1/3.
In that particular case, for that particular origin-destination pair. But again, what we're looking at here is all possible origin-destination pairs based on 4 loop stations as the origins. Okay, so we're looking at each data point here is the market share from between a particular loop origin and non-loop destination, where they have plausible choices. So I'm not going to be able to answer your question directly, but I'm going to explain what's going on. So for every origin-destination pair, we look at the alternative paths in terms of all of those path attributes I talked about. Number of transfers, waiting time, transfer walk time, etc., all the way down. And then we hypothesize a form for the model and estimate the parameters in the model. So it will depend on the preferences of the individual whether they will choose the shortest path, the shortest total time. But if I go back to that, let me just... if I go back to this lists all of the attributes. Total travel time was not an important independent variable in the choice. So what that's saying is people aren't really making their decision. Most people are not making their decision based on total travel time. Where it does enter in a little bit is it enters in terms of length. This is an interaction term. This is the product of in-vehicle time and the length of the trip. Okay? So people trade off value transfers more depending on how long the trip is. The transfer is the same, but they perceive it differently based on how long their origin-destination trip is. Okay? And the other one that showed up as significant was this interaction term here between in-vehicle time and number of stops. So some people, again, trade off the transfer penalty with the number of stops they have on their origin-destination trip. And these are fairly highly correlated. So I can't give you a direct answer. And again, what we found was that there is taste variation, as we would expect. So not everyone perceives a transfer the same way. I mean, people have different levels of ability to walk, to get upstairs, to go downstairs. And clearly that will affect their willingness to transfer. If someone has difficulty or cannot easily negotiate a transfer, then they'll be willing to take a longer trip to avoid that transfer. So more generally, all of these models will do better if you allow for taste variation within the population, which clearly exists. And now we can do that with these discrete choice models. Jim?
Yes, on the path choice estimation, it didn't appear like transfer waiting time had much of an effect.
That's right.
Do you have
Exactly.
an explanation for that?
Yes, I do. The reality is that there's very little variation in the waiting time because all of these loop services are operating at very much the same headway, certainly during the peak and during much of the off-peak. So it's not showing up as a significant variable because it's not really a path-dependent variable. And that's the same for the initial waiting time as well, that you're not getting enough differentiation. So I certainly wouldn't extend that to more general networks. I'm sure that's a very important issue. But in this particular case, there isn't enough differentiation to make it, to show its true importance to travelers. Yes?
What's the average distance that somebody will walk to take transit, and does an urban setting make it more likely they'll walk farther to take the transit or not?
Okay. Nothing I've said here addresses that question, but we have done work. One of the advantages of using smart card data is that if you get permission, you can access the address of the card holder. So that means you then have a true origin and the location they access the system at. And we're doing analysis like that for the CTA Chicago Card Plus, the smart card users in Chicago. So we're estimating and refining the willingness to walk as a function of distance. But again, this is a selected data set. These are the people who not only are using CTA, they're using it often enough to get willing to buy a smart card. So we certainly can't build on that to generalize about this. I mean, it's something that's been studied fairly widely, but I think, again, the smart card data, particularly in London, in London with 2.3 million smart card, Oyster card users, that's becoming the default way of paying for your trip in the London system. So I think we'll get a lot of information from that about willingness to walk. But again, it's still, all of these are conditioned by, these are people who are currently using the system. So to expand that to the population as a whole, which is critical to attract new people to the system. I mean, there are limits to what we can get out of information that's just based on people who are now using the system. Because people who are not now using the system, it's very important for us to attract to the system, will have different perceptions and a different utility function. So this, in no way am I arguing that this can replace general market research and home interview surveys, but I think it can help us narrow the scope and sharpen the focus of those questions we want to answer through those techniques. Yes?
This is going back to the first question a little bit about travel time.
Right.
TriMet has a transit tracking tool where you can type in your origin and destination, gives you your possible routes to get there, what time you need to be there, and then your total travel time. I think even transfer waiting time. So I'm just wondering if CTA has this type of tool to get this travel time information to the user.
Yes, it does. I mean, I think that's another use of the information that comes out of this. I mean, in those tools, you generally don't have a lot of ability to specify your own preferences and constraints. And the effectiveness of the information you're given for you will be strongly conditioned on how much information the tool asks from you to understand your preferences and constraints. So in many of these systems, if you are a wheelchair traveler, then that will be built into the path selection procedure, although not typically in real time. So you don't, if the elevator is out at a particular station, that often is not, I don't know about the TriMet system, it's not functioned into the pathfinding system. But in general, you don't have a lot of ability to express your preferences. And I think ideally what you would want to, where you'd want to go with those systems is to, if you're going to be making use of this system more than once, is to allow you the option of going through a little conjoint analysis sort of state of preference thing, so that the tool can help understand what your preferences are and give you routes or paths which are based on that. That's really what I think you'd want. We're far away from that yet. But so I think we can get information from these sorts of analysis to help refine the trip planners on the web. Yes?
In the case one, in the situations where you didn't have all the information for the buses,
Right.
was the difference in the time of the boarding looked into it all to see, well, how far would they get on the rail in that amount of time to give a clue of where they might have entered, or did you just completely throw out those trips?
At the moment, we've just thrown them out. But you're absolutely right that there are lots of other things that we could do quite logically to try and make as much use of the information as we can. I mean, really, this is sort of a fuzzy logic problem. You've got lots of partial pieces of information, and you've got to try and put this together in some way to form the maximum likelihood origin-destination matrix that's consistent with these observations. So I think what we're presenting here is just the very beginning of really exploiting this data to understand more about what the usage patterns are in the network. And I think your example is a very good one of that. Yes.
You mentioned that some of the single pairs and multiple uses appeared in the data. How many cheats did you identify, or are you able to identify from this system?
We haven't tried to do that. Again, the AFC technology is set up that you can only that will only accept multiple swipes if the card is appropriate for multiple swipes. So if I'm a monthly unlimited use pass holder, then that won't work. There's some sort of time shutdown on not just the individual AFC reader, but all of the AFC readers in that bank, typically. So that if you've swiped your card, then it's half an hour or something before that card can be reswiped, if it's that sort of instrument. But again, there's no reason that if I'm shelling out $30 for a pay-as-you-go usage, and I'm traveling with a friend, that I can't use that. You want them to be able to use that card for the friend because you're paying for it just the same way. And that's typically the way these things are set up. So they're protections, but we haven't looked. The direct answer is we haven't really looked at the cheating rates. Yes, Steve.
I just got a quick question about the using the information for the O&D database. I know
Yes.
I actually talked to Adam, and I think they were
Yes.
interested in using it. I think it's a great opportunity to calculate passenger miles.
Right, absolutely.
But I'm a little worried about the bias towards the rail-to-rail versus the rail-to-bus calculations.
Right, I agree.
And, however, was there any work done on looking at the total distance between those, as far as what was the typical distance between rail-to-rail, the ones you had, versus the bus-to-rail, to see if there was any sort of bias on distance between passengers?
We haven't looked at that. Adam's work, and this is Adam Rabi, who I acknowledged at the beginning, who's been very critical in all of this work and is a pioneer in this area. He's been very much focused on the National Transit Database, making sure that the precision requirements are met and there's no bias in this. And as I think he probably told you, they had a consultant in to actually do the confirmation that this satisfies NTD, and that was successful. So there's the way, but that's not going through all of the, it's not going through the OD inference procedure and verifying that the inferred OD matrix is in fact unbiased. He's looking at a much narrower measure for saying, yes, this is okay. So my view is that it's a big problem at the moment. We need to be able to do a much better job on rail-to-bus movements. That's a very important part, certainly in CTA and many multimodal systems of the ridership. Again, the results I presented were from 15 months ago, January 2004. We're doing this again now for September 2004, and then we'll do it again for a more recent period. But I don't think we're there yet, and I don't think we're ready for the CTA to use this for their own internal purposes. We have to do the validation. We have to get, I think, better coverage on the rail-to-bus inference results. Yes?
So in the beginning you talked about how lots of times when the technology is implemented at the transit system, whether it's the passenger counters or the fare collection, that the technology is being used for just one purpose. And at that point we're kind of getting data and not necessarily information.
Right.
Has research like yours, is that slowly changing the industry and changing the transit agency's perception or, I don't know, ability to get information from these types of technologies, or is unfortunately it just staying the same way?
Well, I think the work that Portland State and TriMet have been doing are changing perceptions of the value of information you can get out of these systems, AVL and APC in particular. I think that, I hope and believe that the work that we're doing with Chicago and Boston will begin to change the understandings of the value of these systems. But I think that it's going to be a long process. And again, people are not going to be persuaded. I mean, people who are very committed to this industry are not going to be persuaded that this makes sense until we can show that there are real benefits. Not that they don't care about whether we can estimate origin-destination matrices. That may be an a worthy academic exercise, but what's the value of that for TriMet or CTA or the MBTA or Transport for London? Until we can demonstrate that, at least hypothetically, and with a strong enough case that people in those agencies who have the operation day-to-day responsibility for that system say, okay, it's worth, I believe this sufficiently to actually change something in the system, then we haven't got there. And I think we're still working up that learning curve. It's not, we were talking about this morning, that in some other meetings, the technology, the automatic data collection systems are, I think, a really helpful step in making a strong case about the value of changing the system. But they just, at best, they tell you what the problems are, and then you have to think about the solutions and how you can implement those in very complex bureaucracies in these organizations. And that's where the real challenge is. The technology is really the simpler part of this problem. But I think it's a necessary part, and I think, again, what TriMet and Portland State and MIT and some of these agencies are doing are helping move along this chain. But it's a long chain, and it's going to be a long process to really have demonstrated credibility. I mean, again, TriMet, Chicago are leaders in the U.S. transit industry in terms of thinking about doing things differently. And so they're the easy part of the industry. And that's a hard battle. It's hard to get any agency, even a progressive agency, to change in a fundamental way what they've been doing for a long time, because every leader has to be to some extent risk averse. I mean, you get hammered, obviously, in the press if you make a mistake. And it's natural to be somewhat risk averse in that context. So it's incumbent on us researchers within the organizations and within academia to make a strong and clearer case for the benefits and the minimization of risks as we can. I think the technology is a very important part of making that case. Yes?
Question kind of going beyond this. Sorry, thanks. Prediction.
Yes.
Being able to, with traffic
Yes.
right now, we're able to predict to a certain level of certainty what traffic conditions will be based on real-time information we have coming out, and then
Right.
either push information out to people or, in some cases, invoke strategies to maybe address a situation before it occurs. Now, I was wondering, on the transit side, your discussions here got me thinking, is there value to a transit agency being able to see, okay, here's what my loadings are starting out at the day and seeing what's happening, and being able to predict what path they're going to take? What could a transit agency do with that type of information? It's more of a kind of a general question. I just want to get your thoughts on that.
I think the problems on the highway side and the transit side are fundamentally very different, because on the highway side, most travelers have many, many path choices in a very highly connected and complex network. So it's more easily apparent where the benefits are of real-time information in terms of, based on predictions of what system state will be in 10 minutes time, half an hour time, whatever it will be, because of the equilibrium nature of the highway system. That's very service quality is very sensitive to volume and to incidents. Now, in public transport, obviously incidents have a tremendous impact, and if the buses are affected by street congestion, then the sorts of prediction techniques that are needed on the highway side are also going to be of value on the public transport side. But certainly in many North American U.S. transit networks, there aren't nearly as many path choices available, and so it's often more a question of saying, now it's not a good time to make this trip. If you can rearrange it so this major incident is cleared up, you'd be better off doing that. Or just, if you have to make the trip now, you should be aware it's going to take you an extra half hour compared with what you're normally doing. It may not affect your path choice. It may affect your departure time choice. So I think, again, depends what the network is, and certainly even in TriMet or Chicago or Boston, there are important path choices going on. And I think you have the same sort of opportunity to provide some benefit there, but I would still expect that generally the benefits would not be as substantial on the public transport side unless there's very close interaction between the highway congestion and public transport travel times.
In the conclusion section, you mentioned about behavior study, and how would behavior study help in the improvement of the system?
I mentioned the behavior study.
Yeah. I think you said there'll be some more research on that.
Okay, let me have it. Well, I'm not sure exactly what you're referring to be honest.
Where the people are more, the transit usage, is it more concentrated in areas where it is, the population is more like in city, in urban settings? And will it benefit the study, will that study benefit the usage of that area, benefit in future to develop other areas?
Yes. Again, I think the principal direct benefit of this work, if you look at it in the future, is that we'll be in a better position to provide better customer information. The trip planner, based on the real-time state of the system, providing better advice on paths where you have path choices in the network. I think that can affect people's decision whether to use public transport. Again, if public transport system is working well and you're providing accurate information, then you want to encourage people to use the system. And I think the sorts of techniques we're talking about here can lead to a more accurate estimation of what your experience will be like on the system, and so it can lead to a lower probability that people will be dissatisfied once they use the system. Again, if the system is not functioning for whatever reason, a major incident or a derailment or whatever it is, it's in your interest to make people aware of that before they make a decision about whether to come out and try and use the system at that time. So in the short run, it may result in lost passengers, but in the long run, it will result in more passengers. I mean, one of the systems I worked on in London was the countdown system, and I know you have real-time information available on your, at least on the light rail system about arrival time of trains. And I think that system is very reliable. But when I was in London working on this, it was a time when the IRA was continually mounting bomb threats. And their intent at that time in the 1990s was not actually to kill people, but it was to disrupt the economy and to make people feel insecure. And in that context, countdown, real-time information at bus stops, was invaluable because you got to a bus stop, you could see immediately if service was suspended indefinitely because there was a bomb threat, or there'd been a major accident down the road, and instead of the 5 minutes you expected to wait, it was going to be 20 minutes. The real benefit of those systems, in my mind, the immediate benefits are people won't use the system because they'll say, I'll take a taxi, I'll walk, I'll give up on this trip for the time being because it's just not. But it improves the satisfaction of those people, even if they're making the short-run decision not to use the system, because their long-run confidence that they're getting accurate information about what their experience will be is improved. So I think there's a tremendous benefit just in terms of customer information and better, a more accurate description of the way the system is functioning at the time you're thinking about using it. No.
Before we thank our speaker, I want to remind everyone that next Friday, the same time, same place, Pat Egan from the Port of Portland will be here speaking about Connect Oregon, which is a proposal by Governor Kulongoski, and I believe there's a legislative bill proposed to be moving forward with a major investment program in multimodal projects that link the waterways and the airways and the freight system with our highway and transit networks in the state of Oregon. So that is next Friday. And so let's give Professor Wilson a round of applause. And after that, hold on. Jennifer Dill's going to do a little housekeeping for the students who are enrolled in this course. So let's thank.
Thank you very much.